Hello everyone, this is Maheshwar Ravuri, a computer science student here at Fresno State. Today I'll be giving a talk about how we are modernizing the planetarium experience using virtual reality. First of all, I would like to thank Dr. Hubert Sakati, my mentor, and the Department of Computer Science for providing me with the necessary tools to work on this project. A quick outline of today's talk is I'll start off with a quick introduction, move on to goals, then methods, and then limitations and implications. To start off, we believe planetariums were great in the 20th century, where they consisted of a dome over the head and a projector in the center, and then a seat surrounding all around it. There are a couple of benefits. They helped popularize space exploration and general interest in astronomy to the general public. But moving into the 21st century, we believe there are a couple of issues with the planetarium. First of all, they show pre-rendered content, meaning none of the data is real time. Is not real data, which means we can't use. It's okay for general viewing purposes, but not for research purposes. And also the projector themselves, it's a 180-degree projection, which means at a time you're losing about half the data that could be displayed. And also the perspective is skewed depending upon how close you sit to the projector itself. Also, there's no individual interaction, meaning as in currently all the planetariums are led by a host. Before we move on to macro, I would like to show a quick demo. So these are all the planetariums in the world. As you can see, they're very densely populated in the North American region, where there are many developed countries. Very few in the South American region. A lot in the European continent. Almost non-existent in the African continent. And they're scattered all over Asia, even though their population levels are way higher than ours in the West. Although Japan and South Korea are like exceptions, where there are many more planetariums. This causes a lack of accessibility, which defeats the purpose of a real planetarium, which is meant to inspire a lot of the public, getting them interested in science and space. And also the infrastructure costs has risen exponentially ever since it was introduced in the 1920s. In the 20s, there were around $70,000 to build a complete facility, but these days they cost upwards of $2 million just for the projector alone. Our goal was to bring the planetarium experience without any of its trade-offs. For that to happen, we had to have accurate data. So anything we visualize must be fact-checked, compared with other tools that scientists use today. It has to be immersive. It has to meet and exceed immersion levels provided by a real planetarium. It has to be very inexpensive, which will help anyone in the world get access to it. It has to be portable, meaning it should be able to be used all by yourself without without you going to a physical place. And it should not be tied down to a single device. It must work on all the devices on the market. And it should be extensible, as in if we wanted to add many more catalogs in the future, they can be added very quickly and without any conflicts. And it should be interactable by anyone ages 10 and up. Our methods consist of 4 stages. Stage 1 was actually collecting star data. Stage 2 is actually visualizing the data in a 3D space. And stage 3 was optimizing it for virtual reality. And stage 4 was to conduct user experience and usability tests. So stage 1, choosing the dataset. We chose the HYG dataset, which basically consists of the Hipparcos, Yale, and the Gliese star catalogs. This dataset gave us enough information about each star, like the magnitude, its name, and its position in the space, and star color. The next step is to actually clean the data and then transform the data. As a couple of tools we used was Python. It is used by many in the community to do data processing and data manipulation. So this is the original data set. It is very detailed and has a lot of information about a star, but we don't require all of it. The first thing we actually need is a color index, so the color of a star. So for that to be displayed in an application, we have to do a couple of conversions. We have to convert it from its color index, basically how blue a star is, meaning how hot it is. The more the blue value, the more hot the star is. But to convert that to a temperature, Kelvin, and then from Kelvin we can convert it to RGB. RGB is basically how a computer displays color. It's a mixture of red, green, and blue values. Next step is to transform the star data. Star data is usually recorded in its right ascension and declination, and we had to convert it to x, y, z coordinates to be displayed in a 3D space. So after all these transformations, we end up with this type of model where each star has its name, its magnitude, and its color, and its position properties. For visualization, we use a tool called Unity, which is used by many in the industry for different purposes, like game development, like 3D game development, or like creating 3D movies. The really good thing about Unity is its particle system. It's usually used by developers to display generate fire as it's random. But what I found out was that each particle has a physical size property, position, and its color that we can change. So what I've done is we took the data that we've seen in the previous slide, and I hooked it to each particle, which ended up with giving us this. So what you see here is every single star in our data set being plotted using the particle system in a 3D space accurately. We are displaying almost 41,375 stars in real time without any performance loss. The next step is to optimize it for virtual reality. This is a virtual reality headset. This is something you wear on top of your head to view the contents. So one thing we had to keep in mind was human-computer interactions. As VR systems do not use a keyboard and mouse, we have to adapt to a controller. So to make sure anyone can use a controller to control everything within the program itself. So one thing is we had to maintain high frame rates. What this basically means is how fast the information is being displayed per second within the console itself. A typical laptop that you may be using right now refreshes at around 60 times a second, or 60 FPS. But it is recommended by the community to get at least 90 frames per second for a virtual reality headset. But in our testing, we were able to get almost 300 frames per second, which drastically reduces motion sickness and eye strain. A couple of limitations we dealt with was we weren't able to get enough user experience and usability tests due to the COVID-19 pandemic. We lost out on getting immersion data, and if it was easy to use, and if it was causing any motion sickness or eye strain, and also testing on different headsets. As we were only able to use one headset, we weren't able to adapt it to. We weren't able to test it on multiple. Implications. We believe that this is a tool that could be used for research purposes by astronomers in the field, and also by amateur astronomers, as all they have to do is provide the data and the tool can automatically visualize it. And we believe this can be used in schools to be promoted without them going on field trips and stuff. and also we believe it can be used for entertainment purposes and also recreational use, or just for relaxing. And I would like to thank the Virtual Symposium Committee for accepting my abstract and allowing me to present at this virtual symposium. These are the references. Thank you.